A fully loaded Boeing 737 weighs around 79,000 kilograms at takeoff. If the runway it rolls down is flat, perfectly, geometrically flat, that plane is in serious trouble the moment it rains. The crown in a runway isn't cosmetic. It's the reason the runway works at all. In this video, why runways are shaped like the world's subtlest hill, what happens to the pavement when you get the slope wrong, how that slope changes depending on whether it's concrete or asphalt, and one famous case where a runway drain failure grounded an entire airport for 2 days. Most people assume runways are flat. That's the obvious mental image. A long, smooth, dead-level strip of concrete stretching toward the horizon. And from 200 meters away, they look that way. But a standard commercial runway is built with a cross slope of between 1 and 1.5%, rising slightly from both edges toward the center line. That's roughly 15 to 20 centimeters of height difference across a typical 45-meter-wide runway. Barely noticeable to the eye, completely critical to the engineering. The reason is water, specifically, the need to get water off the pavement surface as fast as physically possible. Rain doesn't just make a runway wet, it creates a phenomenon called hydroplaning, where a thin film of water lifts a tire completely off the surface and the contact patch goes to zero. At rotation speeds around 260 to 280 kilometers per hour, a 737's tires are spinning fast enough that even a 2-millimeter film of water can break that contact. The crown forces water laterally, off the edges, into drainage channels cut along the runway shoulders. Gravity does the work. The crown is a passive, permanent pump. Civil aviation authorities are specific about this geometry. The FAA's Advisory Circular AC 150-5300-13 sets the cross-slope tolerance for paved runways at 1 to 1.5%, and it distinguishes between the crowned section near the center line and the outer thirds, which can be designed with a uniform transverse slope instead of a peak. This matters because the outer thirds are where aircraft rarely travel. The geometry is designed around where the main gear actually rolls, which on most commercial jets is roughly 7 to 9 meters either side of centerline. Get the crown geometry right in that corridor, and you've protected the aircraft in 99% of operating scenarios. Asphalt and concrete behave differently here, and the crown specification actually shifts between the two materials. Concrete slabs, because they're rigid and don't deform under load, can hold the designed crown almost indefinitely. Asphalt, being flexible, is laid in multiple compacted lifts and can creep over years of heavy use. Rut channels form in the wheel tracks, and if the runway surface degrades enough, those ruts become water traps, linear puddles running exactly where the tires roll. This is why asphalt runways at high-traffic airports get profiled every few years. Airports like Heathrow, which handles over 470,000 movements a year, resurface runway sections on a rotating multi-year schedule, partly to restore crown geometry that heavy Airbus A380s and 700s MM7 freighters have progressively compressed. There's also a structural argument for the crown beyond drainage. The central ridge creates a slight arch in the transverse cross-section. Arches distribute load more efficiently than flat spans. When a main gear bogie, which on an A380 carries 4 wheels per axle on a 6-wheel bogie, rolls down the center line, the crowned geometry distributes that vertical load into the pavement layers at a slightly outward angle rather than straight down. It's a modest effect, but over millions of cycles it reduces the peak stress concentration directly beneath the wheel path. Runway pavement engineers model this using layered elastic theory, and the crown is built into the structural model from the first design iteration, not added as an afterthought. The edge case where this system fails is worth looking at closely. In December 2010, a section of taxiway at Bangkok's Suvarnabhumi Airport was found to have standing water pooling near the center line after unusually heavy monsoon rainfall. Investigation found that the asphalt surface had settled unevenly across several joints, creating a slight inversion, a reverse crown, in a 40-meter stretch. Water that should have drained outward was being funneled inward. The area was near a holding point used by heavily loaded wide bodies, and the repeated loading had compressed the asphalt lifts more at the edges than the center, flipping the intended geometry. The fix required milling the surface and relaying the asphalt to restore positive cross-slope. But the diagnosis took time, and that taxiway section was out of service during peak holiday travel, creating cascading gate delays. A 2-centimeter geometry error caused a multi-day operational disruption. The same logic, crown your surface to shed water fast, appears across every domain where large vehicles operate at speed on paved surfaces. Formula One circuits have transverse slopes of 2 to 3% on straights, steeper than runways because the speeds are higher and the drainage window is shorter. Highway engineers use a standard 2% cross slope on straight sections, and that number has been in road design standards since the early 20th century. Even the decks of aircraft carriers are slightly angled toward the deck edges so that jet fuel, firefighting foam, and seawater drain away from the aircraft rather than pooling under them. The physics is identical. Gravity plus geometry beats pumps and squeegees every time. A runway looks flat because the crown is subtle enough not to be felt during a normal landing roll. But that subtlety is the whole point. Too steep, and it creates a lateral force on a crosswind landing that fights the pilot's rudder input. Too shallow, and water pools where the tires are. The 1 to 1.5% window is an engineering compromise between aerodynamic handling and hydraulic function, and it has been refined over decades of pavement failure data, accident investigation, and iterative FAA guidance. The shape of a runway is not neutral. Every millimeter of that crown is intentional. If this is your kind of thing, the why behind the everyday, object theory drops new ones Monday, Wednesday, and Friday.